Imagine all of space and time, everything you see and touch, compressed into a point smaller than an atom. This tiny, incredibly dense point held all the matter and energy that would eventually become our universe. It's hard to fathom, but that's the essence of the Big Bang theory. This theory suggests that the universe began from this singular point and has been expanding ever since. This wasn't an explosion in space, it was the expansion of space itself, along with everything in it. Space itself was stretching, carrying galaxies with it. Before this event, there was no before as we understand it. The concept of time itself did not exist. Time, as we know it, began with the Big Bang. So what existed before? It's a perplexing question. It's a question that might be impossible to answer with our current understanding of physics. Our current theories break down when we try to look back beyond the Big Bang. Think of an inflating balloon. As it expands, the dots drawn on its surface move farther apart. Similarly, the Big Bang caused the universe to expand, spreading galaxies and stars further away from each other over billions of years. This analogy helps us visualize the expansion of the universe. Similarly, the Big Bang caused the universe to expand, spreading galaxies and stars further away from each other over billions of years. This expansion continues even today. The universe is still growing, with galaxies moving away from each other. The Big Bang theory is supported by a lot of scientific evidence, from the redshift of distant galaxies, which shows they're moving away from us, to the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This afterglow provides a snapshot of the early universe, helping us understand its origins.
What triggered this monumental expansion? What was the catalyst that set everything into motion? The honest answer is, we don't know for sure. The origins of the universe remain one of the greatest mysteries in science. The conditions of the very early universe were so extreme that our current laws of physics struggle to describe them. The temperatures and densities were beyond anything we can replicate or fully understand. However, we do have some leading theories. Scientists have proposed several ideas to explain this cosmic conundrum. One idea is that a quantum fluctuation, a tiny ripple in the fabric of reality, could have been enough to set the universe in motion. These fluctuations are inherent to the quantum world. In the quantum world, particles can pop in and out of existence, borrowing energy from the void. This phenomenon is known as quantum tunneling. Perhaps the entire universe was once such a particle, a minuscule point with the potential to become everything we see today. Another possibility is that the Big Bang wasn't the beginning but a transition from a previous state of existence. This theory suggests a cyclical nature to the cosmos. Maybe our universe cycles through periods of expansion and contraction, with the Big Bang being just one such transition. This idea is known as the Big Bounce theory. Regardless of the trigger, the early universe was an incredibly hot, dense, and rapidly expanding soup of energy. It was a primordial state where the seeds of everything were planted. Within this chaotic environment, the fundamental forces of nature as we know them began to take shape. Gravity, electromagnetism, and the nuclear forces emerged from this cosmic crucible.
In the first fraction of a second after the Big Bang, the universe was an unimaginably hot and dense soup of energy, a chaotic and vibrant mix of fundamental forces and particles. As the universe rapidly expanded and cooled, this primordial energy began to condense into particles, setting the stage for the formation of matter as we know it. First came the fundamental particles like quarks and leptons, the essential building blocks of all matter, emerging from the cooling cosmic soup. These particles existed in a chaotic dance, constantly colliding and interacting in a high-energy environment, a symphony of forces at play. Over time, the universe cooled enough for quarks to bind together, forming protons and neutrons, the core components of atomic nuclei. This period, known as baryogenesis, is crucial because it tipped the balance in favor of matter over antimatter, ultimately leading to the universe we observe today, filled with galaxies, stars, and planets. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to be captured by atomic nuclei, forming the first atoms, primarily hydrogen and helium, the simplest and most abundant elements. This event, known as recombination, marked a significant turning point in the universe's history. The universe, once opaque and dominated by radiation, became transparent, allowing light to travel freely across vast distances for the first time. This ancient light, stretched and redshifted over billions of years, is what we observe today as the cosmic microwave background radiation, a faint glow that tells the story of the universe's earliest moments. The Big Bang itself didn't create life. In fact, it took billions of years for the universe to cool and evolve to the point where life could emerge. Heavier elements, essential for life as we know it, were forged in the nuclear furnaces of stars. When these stars exploded, they scattered these elements across the cosmos, seeding future generations of stars and planets. On at least one of these planets, our Earth, conditions were just right for life to arise. The precise details of how life emerged from non-living matter remain a mystery, but we know that the Big Bang was the essential prerequisite. It provided the raw materials, the energy, and the vast cosmic stage on which the drama of life could unfold.